Hello and welcome to CircuitShepherd. In this video, we will investigate how to utilize CircuitShepherd to design simple, non-inverting operational amplifier circuits. Additionally, we'll take a deeper look into auto parts, custom value sets, and further important features. We start from our voltage divider, which we have designed in the previous video, but before we modify the circuit, let's explore another practically important use case of CircuitShepherd. Since the voltage divider auto part search has delivered acceptable results, we can lock in the resistor values by unchecking the auto option. Now we can ask, which input voltage is required to get a specific output voltage? Let's say we want, for example, 700 millivolts at the voltage divider output. Fortunately, also voltage and current sources can be auto parts in CircuitShepherd. With the default voltage source parameters, CircuitShepherd will search for best-fitting values between -10 and 10 from the E24 series. Apart from the standard E series, we can define our own arbitrary value set or a digital analog converter characteristics, which probably makes more sense for sources. Let's imagine the input of the voltage divider corresponds to a microcontroller digital to analog converter output with 10-bit resolution and 5 volts supply voltage, and define the corresponding transfer characteristics. Once defined, it can be used as a value set for every auto component. For DACs, CircuitShepherd will not only find the appropriate value to fulfill the required design targets, but also the digital value which corresponds to the analog voltage is shown. From an intuitive standpoint, this can be thought of as some sort of reverse voltage divider calculation. This is also the way I like to think of simple non-inverting operational amplifier circuits, as primitive voltage dividers but with input and output swapped. Of course, as with the voltage divider in the preceding video, we can simply fulfill arbitrary design targets by utilizing CircuitShepherd's parameter optimization feature. While the inner resistance of the previous voltage divider was well defined due to the target value of the ohmmeter, the operational amplifier circuit is a little under-constrained here. An indication for missing constraints may be heavy changing auto values due only minimal changes of design targets. A quick fix can be done by simply tightening the limits of an auto part. If you still want to define some sort of inner resistance as a design target, for example, if you want to ensure a precise operational amplifier bias current compensation, be aware that it cannot be done directly in the operational amplifier circuit. For such situations, CircuitShepherd provides the feature of entangled parts, or also called entangled copies. Consider an entangled copy of a part as the same part, or a clone of the part, just used in another wiring context. All potential auto parts can be copied as entangled. Among many other things, part entangling allows us to create helper circuits for additional design constraints and target value specifications, as we do here to specify an inner resistance of the voltage divider used in the operational amplifier circuit. If a part is selected, it can be identified as entangled if multiple reference designators are shown in the action bar. Additionally, the background of the entangled buddies is also highlighted. Before we finish, one last important thing should be mentioned regarding to circuits with multiple target values. Even if you set up a new target value in a way so that it is not in competition with the others, there is a chance that at least some accuracy is sacrificed due to the fact that CircuitShepherd is forced to select auto parts from a discrete set of values. This is the point where it's maybe required to tune the tolerance settings of the target values. In our example, we see that the actual output voltage is much more accurate if we deactivate the target of the ohmmeter. We still want at least some weak bias towards 10 kiloohms, but with a highly increased tolerance, so we don't sacrifice too much of the more important output voltage design target accuracy. Okay, I'd say that's it for now. We've gone through fundamental things needed for operating point-based circuit design. Stay tuned for more in the next videos. Thanks for watching. See you later.